All right, 7.9, rays and radians. In the previous task, Madison's round garden, Madison found a new way to measure angles. Apparently, Madison was not the first person to have this idea of measuring an angle in terms of the arc length, but since she was aware of it, she decided to examine it further. Here are some of Madison's questions, and see if you can answer them. So, number one, since 40 degrees of an angle measures 0.698 radians to the nearest thousandth, and a 50-degree angle measures 0.873 radians, and a 60-degree angle measures 1.047. What angle measured in degrees would measure 1 radian? So we can see that it's probably going to be somewhere between this 1.7, or it will be between 1.047 and 0.873, and we can see also we're going to be a lot closer to this 1.047 than to this, because 1 falls more closely to 1.047 than to 0.873. So how could we figure that out? Well, we could estimate it's probably going to be closer to 60 degrees than 50, but it will be between 50 and 60 degrees. But we want more of an exact number. So last lesson, we found that they are, in fact, proportional. All these things are proportional as long as we're talking about arc lengths and angle measures and the radii rather than areas, right? Because area was quadratic. The increase in area as you increased the radius, but arc length and the angle measures were proportional instead. They were linear. So what we can do is we can actually set up a proportion, right? So I'm going to use just the first one they gave us, 40 degrees and 0.698 radians. And we're looking for, okay, what's the degree measure for 1 radian? Okay, so when we solve for x, we just have to multiply both sides by 1, and anything multiplied by 1 is just itself. So we have x degrees will be equal to 40 divided by 0.698. All right, so I'm going to go ahead and plug that into my calculator. 40 divided by 0.698, and that gives me 57.3 degrees. Okay. So that angle measure is going to be 57.3 degrees, which makes sense that it needs to be between 60 and 50, and it's going to be closer to 60. So now a circle measures 360 degrees, but how many radians is that? Well, we know that the circumference of a circle is 2 pi r, and remember that we're looking at things relative to their radii and their arc lengths, right? So if the circumference of a circle, or the entire arc length of the circle, is 2 pi r, and we know that the radius is r, we can do just like we did last lesson and divide them, right? So it'll be 2 pi r divided by r, and r cancel off, so 360 degrees, or an entire circle, has 2 pi radians, because those radii canceled off. Okay, cool. So the formula Madison's been using to calculate radian measures for an angle that measures n degrees on a circle of a radius r is n degrees over 360, so what fraction of the circle are we working with, times the circumference, 2 pi r, divided by the radius. Okay, but is there a simpler form for converting degree measures to radian measures? Well, let's have a look. Well, again, we see that radius and radius can cancel off, okay? And that gets rid of our denominator down here. It's gone now. Then we have n degrees times 2 pi divided by 360. Well, I see that 2 is a common factor for 360, so I could reduce that, and I would make it then n degrees times pi over 180, just like that, okay? Another way to say this too is n degrees times pi over 180, all right? So here's a simplified version for finding radians. So what formula then might you use to convert radian measures back to degrees? Well, if we have x radians, and we have n degrees times pi over 180. I'm just using this formula that we found up there, or simplified up there, well, now I just need to solve for n degrees instead of for x radians. So if I have even at that variable, all I need to do is get n by itself, so I'm going to multiply by the reciprocal, and I'm going to do that to both sides. So in order to go from radians to degrees, I can just use 180 over pi times my radians. Okay, so simplified one more step, just easier to look at. There we go. All right. So these two things that we just found, there are conversion factors to get from radians to degrees and vice versa. So just like we would use the fact that there are 12 inches in a foot to go from inches to feet and feet to inches, we're going to do the same thing, knowing that there are pi radians in 180 degrees and there are 180 degrees in pi radians. So that is going to be our transitional figure there. So Madison is excited about a radian measurement, and she decides to learn more about it by going online, the internet. To Wikipedia, she finds this statement: an arc of a circle with the same length as the radius of that circle corresponds to an angle of 1 radian. A full circle corresponds to an angle of 2 pi radians. So why is the first statement true? Well, remember that we are looking at angle measures now in terms of their arc length relative to the radius, right? So it's the arc length divided by the radius. Well, if the arc length is equal to r, right? And we're thinking about them as the arc length divided by the radius. When we do that, the arc length divided by the radius, we will get 1. Okay, so there you have it. That is why that first statement is true. So now, why is the second statement true? Well, we know that the ratio of the circumference, right, the full circumference is 2 pi r. And if we relate that back to the radius, which is r, guess what? They cancel off, just like we looked at on the last page. So 2 pi. Okay, so that's why the second statement is true. Madison finds this idea of writing radian measurements in terms of pi appealing. Since circle measures 2 pi radians, she reasons that half a circle, 180 degrees, would measure pi radians, and that a quarter turn, a right angle, would measure pi over 2. And suddenly Madison realizes that while she's been deep in thought thinking about this new idea, she's been fiddling with her protractor. Now her attention focuses on this tool for measuring angles. Like Madison, you've probably used a protractor to measure angles. A protractor is usually marked to measure angles in degrees. Madison decides that she would like to create a protractor to measure angles in radians. So, number 7, we need to label the following protractor in radians using fractions involving pi. So, you can do either converting 10 pi, like for the next one, 10 pi, you can use our formula on the front page to convert from 10 degrees to radians. So here's an example. A ray passing through the 0 and 40 degree angle mark would form an angle measuring 2 over 9 pi, or 2 pi over 9 radians. So we would label the tick mark at 40 as 2 pi over 9. So let's see how they got there, okay? So they started with 40 degrees. Now, how do we get to 40 degrees? Or how do we get to radians from 40 degrees? Well, if you look back at the first page that we were working on, if you have a degree measure and you want to get to radians, you simply multiply by pi over 180, right? And that will give you your degree measures, or your radian measure. These degrees even cancel off, and we call this one radians, okay? So this is our conversion factor, okay? So if we're then, so here we go, 40 pi over 180. Now let's simplify this. So I'm going to cancel off those zeros, those tens. So we have 4 over 18, which reduces to 2 pi over 9. Okay, so we just plugged it in here. Notice that I also kept this as a fraction, right? I didn't divide 2 by 9, and I didn't multiply pi in, because then we start getting numbers that look pretty funky, okay? So instead, keep your answers as fractions using this formula right here, this conversion factor, and then you can go ahead and fill in all of these 10 degrees, right? And we already know, they told us 90 is pi over 2. You can research that on your own if you'd like to use this this formula to get that. You're welcome to, but you can continue doing that all the way to 180 degrees. So that's the last portion of this. Go ahead and take care of that, and then have fun with your RSG.